2, 1, go. Hello and welcome back to Calculus 3, section 15.3 on partial derivatives. So now we are going to learn how to take derivatives in two directions, in x direction and y direction only. And then the next class we will learn how to take derivative in any direction. So if you have some kind of a surface, so let's say this is some wavy surface that is sitting on the xy coordinate plane. We know that there is x-axis and the y-axis and the z-axis, and we also know that this surface is given as z equals f of xy, which is our multivariable function, x and y being the input. I would like to calculate the change along the x-axis. Think of any kind of surface. This is a wavy surface that I am mimicking when I put this microfiber cloth on my hand, right? And imagine now having some kind of a surface like that. You can cut that surface with a, let's say, sword along the x-axis, and that surface will have a trace, a line, right, at the edge of the cut, which goes along above the x-axis. But those are all z values. So that could be some path that it's whatever is the curve. Now that curve is going to have tangent lines, and the partial derivative in the x direction is going to calculate the function that will give us all of the tangent lines along this x-axis. So tangent line at this point, tangent line at this point, tangent line at this point, tangent line at this point. Right, all of these are tangent lines, and those tangent lines, so tangent lines, will have the slope m tangent equal to what we call a partial derivative in x, or partial derivative in x, which we can also denote as the partial derivative of f in respect to x. So these are the two notations that we are going to use. Now, we will utilize the same limit definition with the difference quotient and all that. So fx of xy, which is the first, and we call it partial derivative, fx, is going to be the limit as h goes to 0. And now you have you remember the f of x plus h? Well, you still have f of x plus h, but now you have comma y as well. So we have f of x plus h comma y minus f of xy divided by h. So this is your partial derivative in respect to partial derivatives in x direction. And then we have fy of xy, which is the limit h goes to 0. And it's the same deal. F of x comma y plus h minus f of xy divided by h. So this one is the partial derivative in respect to y. It will give us the slopes of all tangent lines in that direction, in the y direction. Now I am going to show these, two images that the book gives. One is, the first image over here is your hyperbolic paraboloid. Remember the one that has a minimum and maximum at the same point? We call that the saddle point. So you have that shape given here, but now you can see over here the like hiking paths, right? And you have this path that goes east-west, and then you have the other path that goes south-north, right? So east-west path could be your x direction, and south and north could be your y direction. And you can also see that the steepness, right, is what would be measured by the tangent line, the slope of the tangent line. And another nicer image that the book provides right there, as you can see, you have this peak, and then you have the cut, right? So you have some kind of shape like that, and then you go cut it, and the trace between the cut, right, on the surface of the object, and now you can find the tangent line. So that's what these partial derivatives provide. They give you the tangent line, but only in x direction and y direction. How many other directions? Hey, you can walk, right? When you are at the point where that whatever, man, woman, whatever that is, can walk in any direction, not just x and a y. So this lecture is only for x and a y, and then the next lecture on directional derivatives, we can walk in any direction we want, right? So we'll find the derivative in any direction. So now you understand this is the theory, and now we want to actually calculate some of these partial derivatives. So say f of xy, yes, thank you. Say f of xy is given as 3x squared y plus 6x minus 4y squared. You can go ahead and graph this surface. You can come up with whatever you want. I want to find fx, which also can be denoted as partial f partial x. That's another notation for the same thing. So instead of using df dx, now we have this curved d's. This is not number 2. It is a curved d. Instead of having it this way, you curve it that way. So, all right. Partial derivative in respect to x holds y as a constant. One more time. Partial derivative in respect to x will hold y variable as a constant. So we don't get to do the product rule here between two variables. Is x a variable? Yes. Is y a variable? Yes. But if I'm taking the partial derivative in respect to x, y becomes a constant. So I have 6xy as a derivative, because the derivative of x squared is 2x, and since y is the constant, I get to copy it. Fair? Plus 6, because derivative of x is 1, and minus 0, because y is a constant, the derivative of a constant is 0. It's gone. So we don't even need it. Partial derivative of y, which is df dy, is going to be 3x squared. Derivative of y is 1. So 3x squared plus 0 minus 8y. The only derivative that I am taking here is in respect to y. So y is the variable, and x becomes a constant. So as I take the derivative of y is 1, so that's gone. All I'm left with is a constant of 3x in front. So that's my 3x squared over here. This term does not contain y at all, so it's immediately 0. And the last term clearly is what it is. Let's say we have function g of xy given as 3 sine xy plus 2xy cubed minus 4. Well, this minus 4 is going to die for both, right? Because it's constant. Right? So what is the partial derivative gx, which we can also denote as dg dx, but the curved ones because it's partial? All right, so if I am taking the derivative in respect to x, I hold y as a constant. So derivative of sine is cosine, and I have to kick y outside through the chain rule, right? Because it's the y is the constant. So it's going to be 3y cosine xy. Just as a side note, what is the derivative of, let's say, sine 3x? The derivative is 3 cosine 3x, right? So now if this 3 is replaced with y, then these 3's have to be replaced by y. So that's the reason why this y jumps out. Also, xy is the argument of sine, xy remains argument of the sine. So no product rule, because y is not regarded as a function, y is not regarded as a variable, it's just a constant, and you don't do product rule when you multiply constant into a function. So to find the derivative of the first term in respect to x, y is the constant, it jumps out because of the chain rule, and we have 3y cosine xy. Plus, the derivative of x is 1, so this is going to be 2y cubed. Those are all constants. 2y cubed is a constant. X is a variable, derivative of x is 1, so we're done. gy, this is partial derivative of g in respect to y, is going to be 3x cosine xy. Because now, this time around, x is a constant, so you kick that outside of the function. Plus 6xy squared. Because the derivative of y cubed is 3y squared, and then 3 times 2 is 6. Does this make sense? So whatever partial derivative you are taking, keep the other variable constant. Is it constant? Of course it's constant, right? Because you are taking the derivative along the x-axis, and y is always 0 along the x-axis, right? Move it over to y equals, let's say, 1. There is no change in that direction, right? Only the x direction. Let's pick out some exercises from the homework. Okay, this looks sufficiently disgusting. 23. It says S of yz is given as z squared, cross your z's, tangent yz. Because it's going to look like a 2, and then you're going to get confused because there's going to be a lot of them. So what is Sx, which is partial derivative of s in respect to x? Not x, sorry. Y. You're right, actually, the answer is 0 in that. Y, partial y. So for partial y, this z is a constant, and it will jump outside, which would make it immediately z cubed. Z is a constant, z squared that there is constant. Another z is kicked out, and now we have a secant squared, right, derivative of tangent secant squared, and we still have yz as our argument. So we only focus on a variable that we are taking the derivative in respect to, and that variable is the only variable. All other variables become constants. Here is the dreaded sz, partial derivative of s in respect to z. Why is this one dreaded? Product rule. You have a function z times another function that contains z. So we need the product rule. Copy the first, that's z squared, times the derivative of the second, well, that kicks y outside, and the derivative of tangent is secant squared yz. Plus, copy the second, which is tangent yz, times the derivative of the first, which is 2z. If you want to clean this up a little bit, you can. It starts with yz squared secant squared yz as the argument, plus 2z tangent yz. And that would be the partial derivative there in its simplified version. Yes?
The partial derivative of y shouldn't be z cubed y secant squared y.
Partial derivative of y means y is a variable and z is a constant, which means z is the one that gets kicked outside. I know you know this. I'll still write it. The derivative of sine ax is a cosine ax. So the argument stays unchanged, and whatever is the constant gets kicked outside. So when I'm taking the derivative in respect to y, z is the constant, and that's why z is kicked outside. Z squared times z cubed. Because we have second derivative, third derivative, mixed derivatives. So we said today is till 11:15 to make up for all the times when he wanted to go home early. How many derivatives we get to take? As many as we need. The first derivative is velocity, the second derivative is the acceleration, and then jerk, right? So it keeps going. Do I have a second partial derivative? Yes. That would be, so second derivative, second partial. F XX F YY. Same rules. You will take the partial derivative, the first one, and then you will take another derivative to get to the second one, right? So if I have, let's say, z equals three x to the 6 y 4 plus 3x squared minus y, I can find fx, which is partial f partial x, or you can put partial z if that makes you happy, whatever. To find the partial with respect to x, x is the one that we take derivative, so that's 18 x to the 5, y to the 4, plus 6x minus 0. So your first partial derivative, and then you go fxx, which is second derivative of f dx squared, and that would be 5 times 18, right? That's 80. X to the 4, y to the 4, plus 6. So we are able to obtain partial derivative and then the second partial derivative by taking the derivative of the first derivative. Then we move on to fy, which is partial of f in respect to y, and that is 12 x to the 6y cubed. The derivative of y is of y to the 4 is 4y cubed. 4 times 3 is 12. The next term has no y, so that's 0. And then finally I have minus 1, the derivative of y. Now once I have that, I will find fyy, which is the second derivative of f. And that one is going to be 36 x to the 6y squared. Derivative of negative 1 is 0. Can we find the third derivative? No problem. Fourth, fifth, no problem. Get the ones before, you got it. The new feature that Calculus 3 introduces is what we call mixed partial derivatives. So you take the first derivative in x direction, the second derivative in y direction, and the third derivative, let's say, also in a y direction, denoted as fxyy. So the notation will tell you which derivatives and in which order to take those derivatives. So if I want, now here is in red because this is new for Calculus 3, mixed partial derivatives. There was no possibility to have something like this in Calc 1 because you only get to take derivative of the single variable, but now you have 2 variables or 3 or 7. So mixed partial derivatives would be fxy, fyx, fxxy, let's say, and so on. You can come up with literally any combination you want. So, problem. We already have the fact that fx is given as 18x to the 5, y to the 4, right? Plus 6x. See, the next step for me would not be fxx, but fxy, because I want to mix them, right? And the derivative of y to the 4 is 4y cubed, so 72 x to the 5, y to the 3, and the 6x dies completely, because the derivative of 6x in respect to y, right, is gone. Now fy, that we calculated before, was 12x to the 6y cubed minus 1. To find fyx, we had to come up with fy first, and then respect to x. So now, respect to x, 6 times 12 is 72 x to the 5 y cubed. Do we see anything interesting? Do we see anything interesting? They match. And that is a theorem. The order doesn't matter. If you have the same amount of x's and y derivatives, they have to be the same. Right? So, the theorem says that fxy is the same as fyx. Order doesn't matter. Now, this is a really cool theorem because, okay, let's go back and find it. There it is. Look at this beautiful problem, right? If you're taking the derivative in respect to z, you have to deal with product rule. But if you're taking the derivative in respect to y, you don't have to deal with the product rule. So in some cases, the first derivative might kill a variable for you, and then the second derivative you don't have to deal with that variable, which is really awesome. Can I manufacture the problem where we would, let me see. I'm gonna manufacture this problem, yes. Let's say, let me just see, x sine y over x. And we are looking for fxy. Now, if you go in and look for the derivative in respect to x, you have to do the product rule, right? And then y over x in a sign, that's going to give you chain. But if you go and you find fy first, you will have x, and then 1 over x would be kicked outside, and you would have a cosine of y over x. So your fy, partial derivative in respect to y, would just be cosine of y over x. And now you find fyx. So the derivative of a cosine is negative sine y over x, and now you have to take the derivative of the I'm taking derivative in respect to x, right? So that's gonna be y, negative y over x squared in the chain rule. So altogether, y over x squared sine y over x, I believe. And that would be the same as if we did x first and then y. But it's clear in this particular example that y is a better choice for a first derivative because it did not introduce product rule. And in addition, right, it knocked off the x. So the next time we had the derivative, we had the easier time of dealing with it. So you have an option to run x first or to run y first, whatever the problem, right, makes it easy. Whatever makes it easier. So partial derivatives in x and partial derivatives in y, calculate the change in those directions. You can have multiple derivatives. Anytime you're taking the derivative, you keep the other constant, other variable constant, and then be careful with the product quotient chain rules. Obviously, if you have second or third partial derivatives, you calculate those prior. And then if you have mixed derivatives, as long as you have the same amount of x's and same amount of y's, you can do them in any order you like to make sure that the calculations are as easy as possible. Bye. I'll see you tomorrow. We'll do the rest of it. You are welcome.